Hello, Chemistry, Earth, and Space Science. Here we are still in Unit 4, still in Lesson 2 on chemical reactions. We've already seen the first two, synthesis and decomposition, and some subtle nuances to those. Now let's look at single replacement, and then the next video will be double replacement reactions. So a single replacement reaction, which you've already discussed in the first video, is one where you have a element replacing a similar element in a chemical reaction, meaning a metal is going to replace a metal or a non-metal is going to replace a non-metal. And when one element takes the place of another one in a compound, that is called a single replacement. Example might be here where you have element A. Element A might be looks like it's a metal here, and you've got BC, some compound that has a metal and a non-metal. The metals will switch places. This metal will switch places with that metal, B, and B will be by itself now, and A is part of the compound. There's a reasoning why they would switch places called the activity series, and we're going to hopefully dive into that pretty good here in a second. So, typical single replacement reaction, element plus compound gives you an element plus a compound. A plus BC gives you AC and B. That's if A is a metal. And if A is a non-metal, then it's going to swap places with the non-metal in the ionic compound. Swap. So how do we write single replacement reactions? Well, first thing we need to do is determine what our reactants are. Here's a good start. Zinc metal reacts with copper 2 chloride solution. That means I write my reactants, which is zinc, and my copper chloride, copper 2 chloride to be specific. Then I predict what the product's going to be. Now, since the element is by itself is a metal, I know that it's going to kick out, this zinc is going to kick out that chlorine and make chlorine by itself, and the zinc is going to pair up with the chlorines or the chlorides. Metal replaces the metal, and you get zinc chloride, and you get copper. Now, we do have to write the formulas correctly on the right-hand side, just like we did on the left-hand side, reactant side. So we're going to go ahead and make sure we do the crisscross, and don't forget our Brinkelhoffs. Well, Brinkelhoff doesn't apply here because none of the Brinkelhoffs are by themselves. But I do notice that zinc has a +2 charge and chloride has a -1 charge, so there should be a 2 there to balance that out. And lo and behold, when we do that, it actually balances the whole reaction out. When writing your compounds, the new compounds, the cation goes first, the metal goes first in the new compound. Now, this activity series. So when looking at these reactions of metal kicks out metal, not every combination is going to occur. Some metals are much more active, much more wanting to become a ion, turning into the ion, the plus charge, and then through a series of experiments, one of which you'll be able to do as part of your optional lab for activity series, is you can determine, well, which metals are more active than other metals by just mixing them together and seeing when reactions happen and reactions don't. I am getting rid of that sound, sorry. So here is the activity series that we're going to use for this example. There's an activity series in your homework packet to help you out knowing what order they're in. But there's always going to be listed from the top of it. It's going to be the most active. The bottom is going to be least active. The top is going to be the ones that are going to react and form an ion versus the ones at the bottom. And that's kind of good. Look what's at the bottom. We've got copper, mercury, silver, and gold. These are all very precious metals, the ones that are used for money. So you don't want those decomposing and turning into the ions and maybe being flushed away with water. Those guys have a tendency not to do that. That's why those elements were actually used for monetary purposes. So the way this works is first we look at some reactions and see what will work and what will not work. So if I take iron and copper sulfate, and I just have to find on my table here where iron is and where copper sulfate is. Okay, so first thing I want to do is look at my table and say, well, right now I look at the list, and on the right it lists which ones are most active. So if I look at the two, I want to figure out which one is above, which one is going to be most likely to form the ion, to most likely turn into the charged particle. And I see that on this table, if I look at iron, iron is above copper. And since iron is above copper, that means of those two elements, iron and copper, iron, when you're done, when the reaction is done, will be in its ionic form. It will be in a charged form. In this case, it will be iron plus 3. Try again. So they're going to switch places. Second one, nickel. Nickel is below sodium. So at this reaction of nickel with respect to sodium chloride, that's not going to happen because that nickel is less reactive than sodium. Sodium is already in its charged form, always already in its cation form. So sodium is going to stay in its cation form and nothing's going to happen. So if I put some nickel metal into sodium chloride, nothing's going to happen. But if I put a piece of metal, iron, into copper sulfate, I'm going to see a reaction take place. Let's try the next one, lithium and zinc carbonate. So I'm looking for lithium and zinc. Lithium's up there above zinc. And because lithium is above zinc, I know that that reaction is going to occur. The cations are going to switch places, and I get lithium carbonate, and I get zinc, the metal. They swap places, and I get zinc and the lithium carbonate. Remember, right, the formula for lithium carbonate correctly, lithium is +1, carbonate is a -2. One more, aluminum and copper chloride. So aluminum is above copper. That means yes, if the element that's by itself, if the element that's in its elemental by itself state is above the one that's in the compound, then the reaction is going to take place. So if I put a piece of aluminum into a copper chloride solution, I'm going to get aluminum chloride and some copper metal. They're going to switch places. So you can look at an activity series. Again, there would be one in your homework packet that lists the various activities, and it'll be the same one that I'll use on the test quiz that includes the reaction types. So right now, if you notice, these are all metals on the right-hand side, but hydrogen is there. And to be honest, I'll give you the background. Hydrogen is used like as a standard because hydrogen, the ion, is found in acid. So if hydrogen, the ion, is in acid, this will tell you that when acid will react and maybe dissolve some of these other materials. So hydrogen, being that it's starting in its ionic stage in an acid, will react with aluminum because aluminum wants to swap places. Aluminum would want to be in its ionic state. Whereas that same acid, if I put it in a container with copper metal, nothing would happen. So it's like thinking backwards. So if I take zinc and I react with hydrochloric acid, I'm going to get zinc is above. So I'm going to have zinc is going to kick out the hydrogen, but hydrogen by itself is hydrogen gas, Brinkelhoff, H2. Copper and water. So if I take copper and react it with water, which is HOH, has H in it, see, where's copper? Copper is down below hydrogen, so that's not going to happen. Nothing's going to happen because that hydrogen that's in a part of water is not going to react with the copper because it's already in its ionic form, and it does not choose, does not naturally progress towards its ionic form, its its elemental form when it comes in contact with copper. How about calcium and sulfuric acid? So I'm looking again for calcium, it's way up here, and hydrogen. Well, this time around, calcium is above hydrogen. So this is a reaction that will happen. And I'll make the hydrogen gas, and I'll make the calcium sulfate. Calcium is a +2, sulfate's a -2. Don't forget the formula writing. Okay, final. Water reacting with sodium. See where sodium is? Sodium is way up here. Sodium is really, 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 really reactive. It does not like to be in its elemental state at all. It's rare that you find sodium metal in its elemental state. It reacts almost instantaneously with water, almost instantaneously with oxygen. It just does not want to be in its elemental state. So sodium being way above hydrogen absolutely will react, and the sodium will kick out one of the hydrogens and leave you with sodium hydroxide. Again, thinking that water is a H and an OH. So really you're thinking in terms of being an ion, not hydrogen and oxygen, but hydrogen and hydroxide. Some other things about the activity series. All metals have a specific place in the activity series. For simplicity, I'm only going to give you some metals on the activity series, but the activity series I'm going to give you will have not only the order, but will also tell you what ion will form. What ion will form in the process. Metals in the top are more reactive. This means they have valence electrons that are very, very free, have low ionization energy. And on test exams, I'll give you the activity series. Just remember there's going to be potassium is going to be towards the top, being one of the most active metals. So what about the other side of the coin, the non-metals? What if we want to do an anionic replacement reaction? Well, in that case, we have this activity series, and that should look pretty familiar to you, because fluorine, chlorine, bromine, and iodine are in the same order they are on the periodic table. Fluorine is in row 2, period 2. Chlorine is in period 3. Bromine is in period 4, and iodine is in period 5. So this literally is, this activity series is on the periodic table. We're only going to deal with the halogens and how they react with things. Past those, it gets kind of clunky. So if I take those and I think the same way, it's going to allow me to predict whether the reaction is going to take place or not, because the higher on the activity series, the more it's going to want to be in a, sorry, I'm trying to put all these things on the screen. So because for the first one, iodine is below chlorine, and you have to think of this one backwards. It's not going to happen. Chlorine is not going to, iodine, the element, is not going to kick out the chlorine. Again, you have to think backwards on this one. So iodine is below chlorine, which means the reaction is not going to go. You're thinking backwards. Periodic table shows you backwards. It's essentially saying these are in the order of the ones who want to be in that state right there, which is the, would want to be in the ionic state. So fluorine would want to be more ionic, and chlorine, then bromine, then iodine. Well, right now chlorine is already in the ionic state, so nothing happens. Fluorine and bromine, well, absolutely, fluorine is the top of the heap. It wants to become an ion, so when fluorine becomes an ion, it becomes a sodium fluoride, and you kick out the bromine, and you get sodium bromide. That's because sodium fluorine is above. So for single replacement reactions, you have a homework page in your homework packet, which also I will include, like I said, the activity series for you to use for that homework. We have one more video to do. I'll try to get it done in the next 15, 20 minutes. Until then, toodles.